longer, so we join later actually.
Okay, it's all right.
Yes. Mm. So on the background, sir, I would like to share that we have the full registration of 200 participants. So by the time everybody would be joining, AICTE Atal Academy that allows 200 participants per FDP. So
Ah,
out of this 200, 142 are the faculties as well as the professionals, and
oh,
58 PG students that we have in the gallery.
oh, that's really overwhelming response you got.
Yes, sir. Yes, sir. So,
So, sir, on behalf of the entire team from the university and from the department, we warmly welcome you, sir. It's such a pleasure always. However, we are meeting on a digital platform first time probably.
Yes.
But, sir, it's always a pleasure to have you whenever you visit us. It's always a good time. It's a quality time, I would say. And we are thankful and will remain thankful to you, sir, for helping us whenever we are in need. You are always there to support us, all our events. So let's continue this journey of knowledge sharing through your expertise, through your experience, and at a new digital platform, sir. So again, we are all thankful to you, sir, for having you with us and sharing your time with us, sir. Thank you, sir, and welcome, sir.
Uh, Thank you very much, sir. Uh, Very good morning to one and all present over here. Happy Guru Nanak Jayanti and happy Dev Diwali. I would like to thank Civil Engineering Department, Faculty of Technology, Marwadi University, for giving me an opportunity to interact with you. So let us start with our today. Uh, Let me to share the screen.
Sir, meanwhile, sorry to interrupt. Meanwhile, you start sharing your screens and we begin. I request Dr. Tarak Vora to introduce the areas of your interest and a very short brief of as a person of yours with all the participants. So, Tarak, sir, please share very briefly. The person that we have with us, Dr. DP Soni sir, to all the participants. Over to you, Tarak sir.
yes, thank you, sir. So, Dr. Devesh P. Soni is the professor and head civil engineering department at SVIT Vasad, and his total experience is 23 years in academics. He has done his graduation from North Gujarat University, Patna, and a master degree from Gujarat University, Ahmedabad. He has done his PhD from DDIT, Nadiad, in 1995. In 2010. His research interest that includes seismic base isolation, seismic active control of structures, and performance-based design. Sir has published more than 55 research papers in reputed national as well as international journals and conferences. And as Ankur sir has said, the sir is a true academician and he is always ready to share his knowledge with short notice invitation also. So I thank you, Soni sir, for accepting our invitation in such knowledge sharing session. And for participants, initially this is the introduction, then we will have 1.5 hour session and last 10 minutes will be question answer. So whoever is having any question related to content, please post your question in the question answer tab. And at last, we will be answering through sir in last 10 minutes. So thank you, sir. Thank you. And over to you, sir.
Okay, thank you very much, sir. Uh, is my screen visible to all of you?
Yes, sir. Yes.
Yes,
Okay.
sir. It's nice and visible, sir. Thank you, sir.
So, effectiveness of seismic base isolation, which is the topic of our today's discussion. So, starting with the scope of this presentation would be to present the concept of base isolation, means how the base isolation works, then to study why and under what conditions seismic isolation is effective in reducing the seismic forces. And the third objective, the third scope would be to study design of base isolated building. So mainly we can say that the presentation is divided in three parts. Part number one, we will be discussing about the concept of base isolation. In second part, we'll be discussing about why and under what conditions the seismic isolation is effective in reducing the seismic forces. And in third part, we'll study in detail how the base isolated structure is designed. Everyone knows that base isolation is a seismic control strategy, especially passive control system. So let's start with the first part, base isolation. Introduction to base isolation. We know base isolation is a technique of separating the superstructure from the ground in order to reduce earthquake motion to be transferred to the superstructure. In a base isolated building, we know the flexible devices called isolators are introduced between the building and the foundation. So here one figure is there where we can see these are the base isolators, and base isolators are sandwiched in between the superstructure and the ground, so that the base isolators lengthens the time period of the structure that we will see in the next slide. Base isolation results in elongation of period of total system. That means when the base isolation system is installed in a building, the time period, fundamental time period of the structure is increased. That means it results in elongation of time period because of the flexibility of the isolation system. Secondly, it adds damping in the system, because we know that the isolation system either consists of rubber, natural rubber, or it may consist of sliding surfaces. Natural rubber, it has inherent damping. So this damping is added in the system, which dissipates the seismic energy. Similarly, in friction type isolator, because of the friction, some amount of energy is dissipated. As a result, the total energy transferred to the superstructure reduces drastically. So, base isolation also results in addition of damping in this system. Now, let us understand each aspect. First, period elongation. So here we have shown one IS 1893 response spectra with which we are all familiar. It is SA by G is plotted on y-axis and the time period is plotted on x-axis, and the response spectra is presented for three different type of soil: medium soil, soft soil, and hard soil. Now suppose we have one superstructure. Suppose we have one single storied building, fixed base building. And let us assume that the fundamental period of the fixed base building TB is equal to 0.5 second. So that zero point 0.5 time period is shown here, and corresponding to time period, the SA by G value is coming 2.5, 2.5 times the gravitational acceleration. Now suppose if the same system is mounted on base isolation like this, these are the base isolators, then because of the flexibility of isolation system, we know the time period will increase. And suppose the increase in time period is, let us say, 3.5 second. Okay. So here I am taking isolation period is equal to 3.5 second. So here we can clearly see that upon increasing or upon lengthening the time period, the spectral acceleration SA by G value, it has decreased drastically. So in first case, SA by G value that was equal to 2.5 G, and for base isolated building that reduces to 0.33 G. Just for interest, let us take the ratio of that. So 0.33 divided by 2.5, it gives 0.30. Means if the fixed base building is subject to, see for example, 100 kilonewton total force, then the same building when mounted on base isolation will be subject to 13 kilonewton force. So we can say that nearly 90% reduction can be achieved with the help of base isolation. So this is the concept of base isolation, and especially with respect to period of elongation. Okay, see basically there are two aspects. One is period elongation and the second is addition of damping. So period elongation we have seen. Now let us see how addition of damping in this system works. For that, we have shown or we have plotted the response spectra for different values of damping. In IS 1893, it is given for 5%, and one table for damping coefficient is given, and using that table, we have plotted this response spectra. So here we can see that as the value of damping increases from 5%, 10%, 20, 30%, we can see that the spectral acceleration reduces. So when the isolation system is provided, it has its inherent damping, and due to that damping, the spectral acceleration reduces. And when the spectral acceleration reduces, the total base shear reduces, because we know the formula VB is equal to Z by 2 I by R multiplied by SA by G. Okay. So addition of damping also reduces the spectral acceleration, whereas in the next plot, spectral displacement versus period is plotted, right? And different amount of damping is shown. So here we can see that as the value of damping increases, the spectral displacement also decreases. So the base isolation, introduction of base isolation reduces the lateral forces in two ways, one by increasing the time period and the other by adding damping in the system. This is a well-known figure. Majority of you might have seen that on the left-hand side, fixed base building is shown, and on the right-hand side, base isolated building is shown. For base isolated building, we can see that the superstructure entirely behaves as a rigid body. I mean, the inter-story drift is relatively small, whereas we can see very large inter-story drift in fixed base building. So, due to presence of flexible layer, the displacement is mainly concentrated at the isolation level. Here we can see the displacement is mainly concentrated at the isolation level, whereas the inter-story drift is nearly, we can say, it is very small, and therefore the fundamental mode of vibration changes from cantilever type to rigid superstructure behavior. Here we can see the fundamental mode is cantilever type, whereas here we have rigid superstructure mode we can see. Then the next point is effect of base isolation. So base isolation reduce the floor acceleration. Why it reduce floor acceleration? We just see that SA by G value decreases because of increase in damping as well as increase in time period. And reduced floor acceleration induces reduced amount of interstory drift. Second effect, less or there is no damage to the structural members. And the third one, better protection of secondary systems. So similar figure is shown here. It is a conventional fixed base building, and here is the base isolated building. So we can see the displacement is relatively high, and it particularly follows the triangular pattern where the maximum lateral force is at the top and it decreases as we move down. So whereas in base isolated building, the displacement is nearly same at all floors because of rigid body behavior. So we can say that all the floors of base isolated building are subject to nearly equal amount of lateral forces. So building with fixed base experience higher story drift, higher amplitudes during earthquake. whereas building with base isolator experiences lower story drift and lower amplitudes. Now, advantages of base isolation. See, base isolation makes building more functional at design basis level. We know there are three levels of earthquake: service level earthquake, design basis earthquake, and maximum considered earthquake. So it makes building more functional at design base earthquake level and less damageable at maximum considered earthquake level, right? It has 2% probability of occurrence and DBS 5% probability of occurrence. Then from safety point of view, the building becomes more robust against earthquakes. And the third advantage is base isolation is the most reliable and widely adopted concept among all other passive devices. So these are the few advantages of base isolation. Now, having introduced about the concept of base isolation, effect of base isolation, and advantages of base isolation, we'll move to the type of base isolation systems. Because till date, so many isolation systems have been developed. Some of them have got place in actual practice, and still some of the isolation systems are they remain in literature. So here I have tried to collect all types of isolation system which has developed till date, and tried to group in three different categories. Types of base isolation. We have three types of base isolation system, or we can categorize the entire isolation devices into three groups. One is elastomeric bearing. That means the bearing which consists of alternating layer of steel and rubber. This is one class of base isolation system. Second class, rolling bearing, means the rolling balls are sandwiched between two plates, and the entire superstructure is supported on this device. This is called rolling bearing. And the third most advanced type system is sliding bearing, that works on principle of sliding. So there is one slider that slides on a sliding surface having extremely low value of friction coefficient. So these are the three major groups of types of base isolation system. So we'll see each group one by one quickly. The first type, elastomeric bearing. See, this can be further divided into two types: steel reinforced isolators and fiber reinforced isolators. In steel reinforced isolator, the rubber, there is a alternative layers of steel and rubber. So we have three types of system called laminated rubber bearing. So it has one layer of rubber, then other layer is steel, again rubber, steel. This sort of construction is that. We will see the cross section of the laminated rubber bearing in the next slide. Then another popular device is lead rubber bearing called LRB system. It is also known as NZ system because it was developed by England. Then the third type is high damping rubber bearings. So these three devices can be grouped in a steel reinforced isolators. Then another cheap version has been developed called fiber reinforced isolator. As the name suggests, there are fibers. The fibers are reinforced inside the rubber, and based upon their shape, we have two types: rectangular system and circular system. So this is regarding elastomeric bearing. Here is a few photographs of elastomeric type bearing. The first one, A, it represents the laminated rubber bearing, where we can see that the alternating layers of rubbers and steel, they are sandwiched in between the top cover plate and bottom cover plate, right? So this bearing exhibit high damping capacity due to rubber, and due to alternating layer of steel, it has we can say very large axial stiffness, vertical stiffness. So this is called laminated rubber bearing type system. The next system on the right hand side, it is called NZ type system or lead rubber bearing system. The lead rubber bearing system is essentially same as laminated rubber bearing, but we can see there is one central lead core that is inserted that increases the energy dissipation capacity. So in NZ type system, we have alternating layer of steel and rubber with a lead core, central lead core sandwiched. So this lead core acts as a energy dissipation core. It reduces earthquake forces and displacement through dissipation of energy. It also provides resistance to wind. Then steel reinforcing plates provides vertical load carrying capacity, and it also helps to confine the lead core. Internal rubber layers are also sometimes provided, and that provides lateral flexibility to the system. Then another type of bearing is called rolling bearing. See, we have plenty of rolling bearing available. See, the double concave rolling ball bearing. Okay, the figure is there in the next slide. Then there can be circular or elliptical rolling rods provided. Then ball system with restoring property and mushroom type, mushroom shaped basement. Then base isolation with spring and cam system, sloped rolling type bearing, ball in cone bearing, then eccentric rolling isolation system, then non-concentric rolling isolation system, then rolling ball isolation system, and the last one is free circular rolling rods. Okay. See, among this rolling bearing, very few have got place in actual practice, whereas the remaining isolation system has still remained in literature. So this figure shows ball system with restoring properties. So you can see there are two plates, top plates and bottom plate, and balls are provided in between with concave shapes. The concave shape provides restoring force to the system so that during earthquake it restores to the equilibrium position. So as mentioned here, balls are put inside two concave spaces between structure and foundation, and the obvious effect in this kind of technique, that is high stresses are produced in contact area. We can say that this is one of the drawback of the rolling type system. The contact area is very small. Because of rolling nature, the contact area is very small, and due to small contact area there is a high concentration of stresses. So this is one of the drawback of a ball type system or rolling system. Then the third group, sliding bearing, which is considered to be an advanced isolation system that works on principle of sliding. The sliding bearings are divided in three groups: single sliding surface, double sliding surface, and multiple sliding surface. Single sliding surface, as the name suggests, is it has only one surface, sliding surface, on which the slider slides. The example of single sliding surface is this friction pendulum system. Many of us know about this friction pendulum system. Variable frequency isolator. In friction pendulum system, the time period of the system is constant. Whereas in variable frequency isolator, the construction is similar to friction pendulum system, but the time period of the isolation system changes with the isolator displacement because of its particular geometry. Then we have another type called variable curvature friction pendulum system, which is similar to the variable frequency isolator, only the sliding geometry is different. Then sliding concave foundation, then double wedge base isolation device. In fact, it has double wedge, but it has only one sliding surface. Therefore, it is placed in single sliding surface. Then polynomial friction pendulum isolator. Further, this is similar to the friction pendulum isolation system, but here the sliding geometry is defined by polynomial mathematical function. Then variable friction pendulum system. For again, this system is similar to the friction pendulum system, but the coefficient of friction varies along the sliding surface of the isolation system. So constant friction is available in friction pendulum system. Here radius of curvature is constant and coefficient of friction, both quantities are constant. Whereas in variable friction pendulum system, mu varies with the displacement. So mu is a function of displacement x. And a pure friction system, okay, it is a Van Loon friction system in which there is no restoring force. right? The best example of pure friction system is a, we can say, flat rubber or a layer of sand between the superstructure and foundation. So these are the few examples of single sliding surface. Then double sliding surface isolation systems were developed. These are the example: double friction pendulum bearing without articulation. See, double friction pendulum system is same as friction pendulum system. It has two surfaces, top surface and bottom surface. We'll see its cross-sectional view in the next slide. Then multiple friction pendulum system. This is basically same as double friction pendulum system. Double concave friction pendulum system, again it is same. Uplift restraining pendulum system. See, in this type of system, the sliding curvature is spherical, but two rails are provided in perpendicular direction. So that is called uplift friction pendulum system. Then multiple sliding surface. Nowadays, the isolation system has been developed using multiple sliding surface because of adaptive nature. The first one is triple friction pendulum system, and the most recent system, this was developed in 2015, around 2015, that is called quintuple friction pendulum isolation system. So we'll see its figure in the next slide. So this is all about different types of sliding bearings. We know this is friction pendulum system, and many of us may have seen this figure. This figure is shown just to see the dimension of the bearing. A man is standing at the center, and we can see how large the isolation bearing is. This portion, it is called slider. The slider which slides on the surface, and the concave surface provides restoring force to the system. On the right hand side, we can see the operation of friction pendulum system. Right. So these are the few pictorial view of sliding type bearing. On the left side, we can see resilient friction based isolation system. Right. It is called RFBI, resilient friction based isolation system. See, RFBI system is basically a combination of NZ type system and friction pendulum system. Okay. So it gives advantages of both NZ as well as FPS. You know, NZ system is a rubber type bearing and FPS is a sliding type bearing. So we can achieve advantages of rubber bearing as well as sliding bearing in a single device, that is called resilient friction based isolation. The internal construction is similar to NZ type system. So there is one central core, right? And these are the plate sliding rings, right? Then peripheral rubber cores are provided, okay? And two plates are there at the top and bottom. So that exhibit internal friction, right? So we have friction. This rubber provides damping, and central core also adds damping to the system. So this is called friction based isolator, right? So it consists of a set of flat rings which can slide on each other with central rubber core and peripheral rubber cores. Okay. So it combines the beneficial effects of friction damping with that of resiliency of rubber. Right. So this is one of the system, RFBI system. Then second one, this one, it is called double friction pendulum system, DFPS, where you can see there are two surfaces, top surface and bottom surface. The radius of curvature can be equal or it can be different. And the two surfaces, concave surfaces, are uh, sandwiched, uh, which carries the slider. This is slider, articulated slider. So there exists friction on this surface, this particular surface, and the another surface where the friction is experienced is this top surface, right? So it has two frictions, coefficient of friction mu1 and mu2, and two radius of curvature r1 and r2. Then the next advancement is TFPS, triple friction pendulum system. Okay. Here you can see there are four sliding surfaces, right? 1 and 4, they are called outer sliding surfaces, and second and third surfaces are called inner sliding surfaces. Now, usually the coefficient of friction, that is mu3, and that of second surface mu2, and radius of curvature r3 and r2, these two are kept equal, means r2 is equal to r3 and mu3 is equal to mu2. So we can model the double surfaces with single surface. It is because of equal properties of isolation system. So 2 and 3 can be modeled using only one surface, right? So now we can say that there are three surfaces. The first surface is number 1. The second surface is the equivalent surface of 2 and 3. And the third surface is surface number 4. So essentially we have three surfaces. Therefore, it is called triple friction pendulum system in spite of having four sliding surfaces. Similarly, QTFP, quintuple friction pendulum system. This is the latest advancement in sliding base isolation system where there are six surfaces, right? 1, 2, 3, 4, 5, and 6 surfaces. So it is improved version of triple friction pendulum system, and this can be modeled using five surfaces. Therefore, it is called quintuple friction pendulum system. QT stands for quintuple, and this friction pendulum system. So this is all about the sliding type bearing. Now, it is essential to understand the dynamics of base isolated building. And here we have taken minimal mathematical formulation so that we can understand easily the dynamics of base isolated building.
Uh, Hello, sir. Your voice is low actually.
Hello, am I audible?
Yes,
Yes,
sir.
sir.
Now
Now
we are.
it is audible, sir.
Okay, okay.
Ji, sir.
So the dynamics of base isolated building is explained with the use of laminated rubber bearing type system, which can be modeled as a linear isolation system, so that we can use response spectrum of method of analysis. Otherwise, for non-linear bearing, we cannot use response spectrum method of analysis. Okay, so here is one building. On the left side, we have fixed base building. This is fixed based building, and the stiffness is K and damping is C, and the mass is equal to M. Now the same system with same stiffness, damping, and mass is mounted on base isolation. So here you can see this is isolation system, and it is resting on base slab. The mass of base slab is MB, and the stiffness of isolation system is KB, and damping of isolation system is CB, right? Now, one thing which we should note, that the lateral degrees of freedom of fixed base building is one only. Here we can see on the floor we have 1 degrees of freedom. However, when the same system is mounted on base isolation, the degrees of freedom increases by 1. Now it has become 2 degrees of freedom, D1 and D2. The displacement at the level of isolation, they will call isolator displacement, right? They will call isolator displacement, and it will be shown by XB symbol. X stands for horizontal displacement and B stands for base isolation level. Then we also know the formulas for calculating the time period and stiffness of the system. Okay, for this particular example, we have selected the fixed base time period as 0.4 second. TF is equal to 0.4 second, and the damping of the system is 2%, because we have assumed that the frame is made out of steel. Now, when the same system is mounted on the isolation system, the time period has increased to 2 seconds. From zero point 0.4 second to it has now become 2 seconds. And due to the damping of isolation system, the damping coefficient has now become 10%. We have assumed that 10% rubber damping of the isolation system, and it is also assumed that the base mass is equal to 2/3 of the mass. It can be anything, that depends upon the design, but here we have assumed that MB is equal to 2m/3. Now, let us move to total isolator stiffness. Okay, see, it's a very simple formula. K is equal to m omega square. This is K, this is m, total mass of the base isolated system, and this is omega. K is equal to m omega square, omega equal to 2 pi upon Tb. So here we have substituted values of Mb is equal to 2m/3, and isolation period Tb is taken as 2 seconds because it was 2 seconds. So upon doing simplification, we get 16.45 multiplied by m. So this is the isolator stiffness. The isolator stiffness is calculated in terms of floor mass. Then we have stiffness of one-story building, that is fixed base stiffness. Same equation is used, K is equal to m into omega square, but it is for fixed base, right? The first one is for base isolated building. So we got stiffness is equal to 246. Okay, these two numbers says many things. Okay, since isolator is a flexible layer, it has low stiffness compared to the superstructure, right? 246 and this is 16.45. Then damping constant of fixed base building, that is, we know C is equal to 2 xi m omega. This is omega. So it comes out to be 0.628 m. And the damping constant of the base isolated building is same formula is used. C is equal to 2 xi m into omega. Xi is zeta b, mb plus m total mass, and this is omega b. So it gives damping is equal to 1.047. You can compare these two values, right? So we have calculated the isolator stiffness, isolation damping, similarly superstructure stiffness and superstructure damping. Now we'll perform the response spectrum analysis of base isolated building using say that is RSA method. So first step, construct mass matrix, stiffness matrix and damping matrix. Since degrees of freedom of base isolated building is 2 for this example, so the sizes of mass, stiffness and damping matrix would be 2 by 2, even though it is a single storied building. So this is the mass matrix, stiffness matrix, here we can write K1 plus K2, then K2 minus K1 minus K1, like similar formation has been carried out for the computation of stiffness matrix. Then here is the damping matrix. Okay, earlier we calculated CB and C is equal to 2 xi m omega. So in this way, we get the mass, stiffness and damping matrices. Then in second step, we have to perform the eigenvalue analysis. In order to calculate mode shapes and natural frequencies, we have to perform the eigenvalue analysis. So upon doing eigenvalue analysis using standard methods, the natural frequencies coming as this, then the time period are this, and the mode shapes are mentioned here. So let's discuss this. The first mode natural frequency is 3.104 and this is 25.1374 radian per second. Okay, this number gives you insightful result. The first mode period is 2.024 second and the second mode period is 0.25 second. So here we can observe that the first mode period of base isolated structure is nearly equal to the isolation period of the system. Okay, you remember that the isolation period of the system was 2 seconds. TB is equal to 2 seconds. And after carrying out the eigenvalue analysis, I mean, after putting the values of mass, stiffness, we got the first mode time period as 2.02, which is same as the isolation period of the system. Okay, so we can say that the first mode is essentially the isolation mode. Okay, that we will see in the next figure. And these are the mode shape, right? It is a first mode shape and this is second mode shape, which is shown here clearly. So first mode shape, you can see this value is 1 and this value is 1.041. So we have plotted 1 and 1.041. Here we can see that the interstory drift is very small. I mean, interstory displacement is very small. We can say it is negligibly small. But the main, or I mean, the total displacement is concentrated at the isolation level only. You can see this is fixed point, and here you have one. And we can also see that the superstructure is behaving as a rigid body, right? It is because of very small amount of interstory drift. So this mode is called isolation mode, that we should keep in our mind, because the displacement is concentrated at the isolation level only. There is no relative displacement in the superstructure, and the time period of isolation mode is nearly equal to the time period of the bearing. Whereas in second mode, you can see there is large amount of interstory displacement. You can see that is equal to 1.641. It is considerably high, right? So in second mode, you will see the displacement in structure. Therefore, it is second mode is called structural mode. So if it is multi-storied building, then the first mode is called isolation mode, and the other mode, that is 2, 3, 4, 5 mode, they are all called structural modes, right? So this is regarding the interpretation of eigenvalue analysis. So second step is over. In third step, we need to calculate generalized mass, generalized damping, and modal participation factor as we do in normal response spectrum analysis. So generalized mass is calculated using this formula, 5 transpose m into 5. So using this formula, the generalized mass have been calculated. M1 is equal to this and M2 is equal to this. So next, generalized damping is calculated using this formula, right? So C1 is equal to this and C2 is equal to this. Okay. Now the most important thing is modal damping ratio. We know this equation for modal damping ratio because it is C is equal to 2 xi m into omega. That equation is written. So let us examine the modal damping ratios for this case. Zeta 1 is equal to 9.664 percentage. Here one number represents first mode. Modal damping ratio in first mode. We know first mode is isolation mode, right? And in isolation mode, the displacement is concentrated at the level of isolation bearing. So the first mode damping ratio is again same as 10% damping of the isolation system. Okay. Obviously, this should be same. Okay. So 9.64 is approximately equal to 10%. This also implies that the first mode is for displacement at the isolation level only. Whereas in second mode, it is structural mode, we got 5% damping. Okay. So in this way, the generalized damping is calculated. Then modal participation factor. Okay, so just using the formula, we can arrive at the modal participation factor. So the relative value of modal participation factor says many things. You can see the contribution of first mode is around 0.976. We can say 97%, and that of the higher mode is just 2.38%. Then what do? We use the design spectrum, right? In design spectrum, we have shown only two spectrum. One is for 5% and the other is for 10%. Why 5 and 10% are taken? Because zeta 2 was nearly equal to 5% and zeta 1 first mode damping was nearly 10%. So we have selected two graphs, 5% and 10%. You can notice that it is independent of the damping of the superstructure, which was considered as 2%. Now, the first mode period after doing eigenvalue analysis, it is coming 2.024 second, and corresponding value is 0.538 G. Okay. Note that we have used second curve. Second curve is for 10% damping, right? And T1 is the first mode time period, which is equal to the isolation period, right? And for superstructure, T2 0.25, and SA by G value is equal to 2.5 times G. Okay, note that here we have selected the 5% damping curve because second modal damping is 5% and the first modal damping is 10%. So using this, we can calculate the value of spectral acceleration. That means this value, we can see this value, and this is 2.5, it is okay. So that two values are mentioned here. It is 0.538 G, and for second mode it is 2.5 G. Right? These are the zeta value and these are the time period value obtained from eigenvalue analysis. Now this spectral value will be used for further calculation. Means fifth step is calculation of response, in which we will calculate the displacements, modal displacement. See, the first mode displacement is 96 millimeter and 100 millimeter. Okay, 96 millimeter is at isolation level. Okay, so when we look the structure like this, 96 millimeter displacement is over here and 100 millimeter displacement is over here. So we can say that there is only 4 millimeter interstory drift. Similarly, second mode displacement comes out to be this. Okay, it is very small, we can see, right? But when we take the relative value, it is around 0.28 millimeter. So second mode displacement is obtained. Then equivalent nodal static force can be calculated using this formula. Okay, we are familiar with this as it is similar to the formula given in IS code. So equivalent nodal force is in first mode is this, and that in second mode is this. Again, you can see that the equivalent nodal force is in first mode is relatively higher than that of second mode. That shows the contribution of first mode. Okay. Uh, the contribution of first mode is significant for base isolated building. So base shear in first mode is this, right? And base shear in second mode is this. Obviously, it is this value for first mode and second mode, right? Now here we have summarized the responses, which says many things. See, the first two column, this is for fixed base building, and the third column is for base isolated building, right? So base shear in first mode is 0.099, or we can say 0.1, and base shear in second mode is very small, right? And SRSS value, square root of this plus this gives you 0.0099. So this clearly shows that we can omit the second mode. In other words, we can say that we can only consider the isolation mode. Okay. Then isolation displacement. Isolator displacement in first mode is 96.4 millimeter, and isolator displacement in second mode is just 0.17 millimeter. Okay. And the SRSS value is 96.4, which is same as the displacement in isolation mode, right? So uh, this is regarding isolation. Okay, by mistake I wrote here, I, I had to write this is for base isolated building and this is for fixed base building, right? Now for fixed base building, uh, the base shear is 0.63. Okay, now let's compare these two value, 0.63 for fixed base building and 0.0099 base shear for base isolated building. So we can see that there is a huge reduction in base shear for base isolated building. So this is what the table says, right? Now we have seen that for base isolated structure, there is very small interstory drift, or the superstructure behaves as a rigid body. So we can assume superstructure to be rigid. So what is advantage of doing this? We can reduce the multiple degrees of freedom system into a single degrees of freedom system, right? Suppose we have five-storied building mounted on base isolation. So the total degrees of freedom is 5 plus 1 is equal to 6. But if we model superstructure as a rigid body, then the degrees of freedom reduces to 1 only. Okay. So we can assume the superstructure to be rigid. And here one example is given. Suppose the isolation period is 2 seconds and zeta b means damping of isolation is 10%. So that the pseudo acceleration SA by G value is equal to 0.544, because from time period we can easily read SA by G value from the response spectrum. Then isolator displacement U can be calculated using this formula. Okay, it is a well-known formula of acceleration is equal to omega square into displacement. So that formula is used. So displacement is equal to acceleration upon omega b square. So UB is coming 0.097 millimeter. Okay. So this displacement is obtained by assuming superstructure to be rigid. So we can put assumption of rigid superstructure without loss of accuracy for certain type of structure, not for all. So with this, we have finished the first part of our presentation, that is the concept of base isolation. Now, second part. In second part, we'll discuss the effectiveness of base isolation. We have taken two cases to understand the effectiveness of base isolation. What I mean to convey is base isolation is not effective in all conditions. Sometimes it may be ineffective. One is the example of soft soil. Okay. See, one response spectra obtained on soft soil is plotted in this figure, right? We know that the normal shape of response spectra, it is something like this. When we plot response spectra of earthquake ground motion, it is like this. Means initially you will get high value of spectral acceleration, and then as the time period increases, the spectral displacement decreases. This is typical nature of response spectra obtained from earthquake measured on hard soil or medium soil. But when we plot the response spectra measured on soft soil, it has nature something like this. Initially, we have lesser amount of spectral acceleration, and upon increasing time period, the spectral acceleration increases. So it's a typical nature of response spectra obtained from soft soil. So just by inspecting the shape of response spectra, we can say that it is for hard soil or soft soil. So one typical response spectra is shown here, where you will see the similar pattern. Initially, we have small amount of spectral acceleration, and at a large period, we have higher value of spectral acceleration. It is plotted for three values of damping: 2%, 5%, and 10%. Now, suppose the same building with a zero point 0.4 second time period, 2% damping, and two-thirds of the floor mass as a base mass. Isolation period is again taken same 2 second, and zeta b is 10%. On the right side, the eigenvalue analysis, I mean mode shape and natural frequencies are shown. It is same because the structural properties are same. Okay. So here we can see that the fixed base time period is 0.4 second. Okay. So 0.4 second time period is here. Okay. TF is equal to 0.4 second. What is spectral acceleration? SA by G value is equal to 0.25 G. This is for fixed base. So I will simply write spectral acceleration for fixed base building. Now, when the same building is mounted on isolator, its time period is increased to 2.024 second. So for t is equal to 2 second, zeta b is around 10%. So we have used the third plot, right? SA by G value, spectral acceleration for base isolated building, it has now become 0.63 G. Okay. So here we can see the spectral acceleration has increased rather than expected decrease in the acceleration. Okay. So in this case, it is clear that base isolation is not effective. Rather, base isolated structure will amplify the response, right? See, everything is same. Structural system is same. Isolation system is same, but the soil condition is different, right? So it is due to the typical nature of response spectra measured on soft soil. Okay. The ratio is shown here. The ratio is 0.63 divided by 0.25 G, it is equal to 2.52. Means base isolated structure will experience 2.5 times more force as compared to the fixed base building, right? So here it seems total foolishness of using base isolated structure for soft soil. So this is the one condition in which the isolation system is not effective. Further, I would like to highlight uh, a typical response spectra for the recent Gorkha earthquake in Nepal. Okay. See, here is the response spectra. Okay. It is unique type response spectra, right? Where you can see initially there is a high value of spectral acceleration, then some moderate value of spectral acceleration, and upon increasing the time period, further the spectral acceleration has increased. So this type of earthquake causes damage to short period structure as well as long period structure. Okay. So if we go for base isolation system for this type of earthquake, then again the isolation is not effective, right? So it's a unique nature of response spectra where you will see hump at the long period as well as at the short period. Then second case of ineffectiveness of base isolation, rather we should say flexible superstructure. For flexible superstructure, we can see that the fixed base period is now taken as 2 seconds. Earlier it was zero point 0.4 second. Now we have made the superstructure flexible. So TF is equal to 2 seconds and damping is same 2% and base mass is again same. Isolation period is again taken as same 2 seconds, right? The mode shapes are shown here. Okay. Here we can see that at the top we have displacement of the order of 2.291 second, we can say, and for the second mode we have 1.291 relative displacement. Time period and everything is shown. Now let us see what happens to this. Fixed base time period is 2 seconds, right? So fixed base time period, follow this. Fixed base time period is 2 seconds and damping is equal to 2%. So we will follow black color graph. For that, the spectral acceleration value is equal to 95 G. Okay. Then for first mode, 2.664, where damping is around 10%. So we will follow this blue color line. Here damping will be achieved as that is equal to 13%. Okay, because of the flexibility and isolation system, zeta 1 isolation damping in first mode would be around 30%, 13%. So we have followed this blue colored graph, right? And for that you will get some value of spectral acceleration. And for the next 0.949, here is the value of spectral acceleration, right? 1.07 G. So here we can see that 0.95 G was the spectral acceleration for fixed base building, and for base isolated building it has become 0.51 G, right? For first mode base isolated building, it has reduced to 51. Of course, there is a reduction in spectral acceleration, but not significant, right? It is not significant. Comparing it with previous example where we could achieve 87% reduction for base isolated structure, that sort of reduction is not achieved. It is because of the flexible superstructure, right? The normally high-rise building are already flexible, and when they are placed on isolator, they are becoming more flexible. So that doesn't give any advantage in terms of spectral acceleration. Rather, it increases the interstory drift and user discomfort. So these are the two spatial area in which the isolation is not effective. One is flexible superstructure, and the other is structure mounted on soft soil. Okay. Here some computation part of flexible superstructure is shown. right? The total base shear, SRSS base shear of a base isolated structure is zero point 0.1 and the fixed base period is 0.171. Fixed base shear is this 0.171 W, right? Obviously, there is a reduction in base shear for base isolation, but the reduction is small. It is not significant. Therefore, it is not suitable for flexible superstructure or high-rise building. Then base isolation for multi-storied building, right? Here, multi-storied building, say of the order of say five storied or 5 to 7 storied is shown. Similar fixed base building is placed on isolation system. The fixed base period is 0.5 second and that of isolation period is 2 second, right? Typically, we have taken friction type isolator for this example, having coefficient of friction is equal to 0.05 and superstructure damping is assumed 2%. Okay. Here, we'll just study the modal properties of fixed base multi-storied building and isolated multi-storied building, right? So let's see the first fundamental time period of fixed base building, that is 0.5 second, and effective modal mass is equal to around 88%, right? This is the first mode of fixed base building. Now what happens to the first mode of base isolated building? We can see first mode, the time period is 2.041, which is nearly equal to the isolation period, and first mode mass is nearly 100%, right? 99.93. So only first mode is sufficient to obtain the response, whereas in higher mode you can see higher mode contribution is extremely small. This is the point which we need to understand for dynamics of base isolated multi-storied building. Okay, then we will look at how the dynamic analysis of base isolated building is carried out. We will move too quickly through this slide. You know, equation of motion is this. It's a well-known equation, mx double dot plus cx dot, okay, plus kx minus m into x double dot b plus x double dot g. We are familiar with this equation, right? So the first equation is for superstructure. Usually in the analysis of base isolated structure, we write two equations, right? One equation for superstructure, right? And one equation at isolation level. Okay. So for all floors, we have one equation, it is this. And for isolation floor, we write another equation because it is resting on the isolation system. So we have to take into account the non-linear forces, stiffness forces, damping forces, etc. So that equation something looks like this. Nature is same, mx double dot plus cx minus cx1 minus kx1. Fb is the isolator force, right? So this equation is written for the base mass. Then for base mass force calculation, we use this equation. It is basically equation for lead rubber bearing, right? And for friction pendulum system, we use this equation. It is the model of lead rubber bearing. These are the three components: stiffness component, damping component, and hysteretic component, which has resulted from yielding of the lead core. Whereas in friction pendulum system, we have two components: stiffness component and friction component. So restoring force in lead rubber bearing is obtained using this equation, and that in friction pendulum system is obtained using this formula, where Z is a hysteretic component which can be solved using popular Markov hysteretic model, giving this first order differential equation. See, in this dynamic analysis, we have assumed that the isolation system behaves in a non-linear way. So all non-linearity has been considered in this formulation. Then after taking the structural configuration and structural data, isolation data, etc., here we have selected the earthquakes. Typically, spectrum compatible artificial earthquakes have been selected to obtain the response of the structure. On uh, top side here, you will see ground motion, earthquake ground motion. It is artificially generated ground motion, The earthquake ground motion is generated in such a way that when we obtain response spectra of this earthquake, it matches with the IS code response spectra, right? For all the three types of soil condition, it matches with the IS code based response spectra. So this ground motion is called spectrum compatible ground motion, and this ground motion is used to obtain the response of the base isolated building. So three quantities are plotted: top floor acceleration, isolator displacement, and base shear. Right? Two graphs are superimposed. The green color graph, it shows fixed base response, and the red color graph shows base isolated response. So we can see that the top floor absolute acceleration for fixed base structure is 2.046 times gravity, and that for base isolated structure is 0.43. So large amount of reduction in top floor absolute acceleration can be achieved using base isolation. Then isolator displacement. Isolator displacement is found of the order of 81.3 millimeter. That is 8 centimeter isolator displacement is observed for this example, right? So whatever reduction in top floor absolute acceleration and base shear is there, they are at the cost of displacement concentrated at the isolation level. So the third graph shows base shear value, right? The base shear for fixed base building is 1.14, and that for base isolated building is 0.13. Again, huge reduction is achieved in the amount of base shear. So this three figures shows calculated response obtained from time history analysis and considering the non-linearity of the structure. Okay, whereas in previous discussion, we use response spectrum method of analysis in which we assumed the isolation system as a linear isolation system. Okay, however, we have considered non-linearity over here, and for non-linear isolation system also the results are nearly same. Okay. This is a typical hysteresis loop of a friction pendulum system, right? Hysteresis loop is nothing but the force deformation behavior. And we can see that the area enclosed by hysteresis loop is equal to the amount of energy dissipated in friction. Because area is nothing but the multiplication of force and displacement. Force into distance, that is equal to work. Force into distance is equal to work, and area under the loop represents the amount of energy dissipated through friction in each cycle of vibration. So larger is the area of loop, larger is the energy dissipation, and larger reduction in base shear and top floor absolute acceleration. Right. This particular graph is for actual earthquake, El Centro, well-known 1994 earthquake excitation. Okay, the previous graph were for spectrum compatible ground motion. It was artificially generated, whereas this graph represents the actual earthquake response under El Centro ground motion, and similar trend is observed. We can clearly see that blue color is for base isolated and green color is for fixed base building. Both deck acceleration and pier base shear has been decreased significantly, and bearing displacement is shown here. Typically, this graph is plotted for bridge, and in the next slide, we will show where the isolation bearing is provided. Okay. So this is regarding isolation of bridges, and in bridge, the isolation bearing is provided between the deck and piers as well as between the deck and abutments. Okay. So next figure shows mathematical model in which the piers are idealized using finite element, deck is also idealized using finite element, and 2 degrees of freedom is considered at each node. Okay. And here is the typical example for earthquake ground motion. Deck acceleration has reduced to 0.085 for base isolated bridge from 0.319 to fixed base bridge. Similarly, drastic reduction in pier base shear is observed. It has become 0.045 from 0.112, and the bearing displacement is equal to 54.7 millimeter. Right. So again, I am repeating, this reduction in base shear and deck acceleration is available at the cost of displacement at isolation level. Okay, there is no such large displacement in fixed base structure, especially in case of bridge. Now, the isolation technology can also be extended to liquid storage tank, nuclear reactor, etc. So here one example is given for isolation of liquid storage tank. You know, liquid storage tank, the liquid of which can be divided into three separate mass: sloshing mass or convective mass, then impulsive mass, and then rigid mass. If the wall flexibility is not taken into account, then we can split the liquid mass into two parts: sloshing mass and impulsive mass. But if we take flexibility into account, flexibility of tank wall into account, then uh, we can divide the liquid mass into three parts: sloshing mass, impulsive mass, and the third mass, rigid mass. Rigid mass moves as rigid body. The rigid mass adheres with the side wall and it moves as a rigid body during earthquake. So MC is the convective mass, MO is impulsive mass, and MR is the rigid mass. And corresponding stiffness is convective stiffness, impulsive stiffness. Since MR is a rigid mass, this stiffness is infinite. It adheres with the side wall and it moves as a rigid body. So right hand side figure shows the mathematical model of liquid storage tank, base isolated liquid storage tank. And in the next figure, the response of base isolated liquid storage tank is plotted, and we can achieve the same thing. You know, base shear, there is a huge reduction in base shear, right? It is 0.25 from 0.625. Then convective displacement. See here, the typical nature of base isolated water tank or liquid storage tank is the convective displacement increases to some extent. Okay, see the 1520 value is for fixed base building, non-isolated. Correct. Green color graph is for non-isolated, that is fixed base. And for base isolated, the convective displacement is increases. Right. It has increased just by 500 millimeter, we can say. But you will see there is reduction, huge reduction in impulsive displacement, base shear, right? It has become 2.25 from 7.48, and base shear is reduced again drastically. So we can achieve significant reduction in base shear and impulsive displacement at the cost of increase in convective displacement. Okay, so we can accommodate empty space above the free liquid surface. We can keep sufficient empty space above the free liquid surface to accommodate the convective displacement, but the structural properties can be reduced drastically when the system is mounted on the base isolation. Okay, so this is regarding response of base isolated liquid storage tank mounted on friction type base isolator. It was subject to Al Centro Area 5 earthquake ground motion. Then another important aspect of seismic base isolation is seismic isolation for near fault earthquake. Okay. Many of us might be knowing about near fault earthquake. However, in order to clear the concept of near fault earthquake ground motion, here two ground motions are plotted. Okay. On the left side, I mean this particular earthquake is recorded for Rinaldi receiving station of 1994 14 for North Ridge earthquake. Whereas right hand side graph, it represents the Al Centro 1914 Imperial Van Loan earthquake. Right. Now, in the next, I mean, below the acceleration ground motion, we have plotted velocity time history, right? Velocity time history can be achieved or it can be obtained by simply doing mathematical integration of acceleration time history. So by doing so, we have obtained the velocity time history for both earthquake, one for Rinaldi receiving station and the other for Al Centro ground motion. Now let us examine the characteristic of the left hand side earthquake, particularly in velocity. Okay, see, in velocity history, you will see a distinct pulse of large velocity. Okay, whereas no such pulse is observed in the right hand side. Okay, see, the right hand side earthquake that was measured far away from the epicenter. Okay, it is called far field earthquake, whereas this left side earthquake, Rinaldi receiving station earthquake, it was measured close to the epicenter of the earthquake. So in this earthquake, we can see there is a clear pulse, distinct pulse of relatively large velocity. Okay, the magnitude of velocity is of the order of 1 meter per second or large. Whereas here you can see the maximum velocity is less than 0.5 meter per second. So the existence of high velocity, long duration pulse is the characteristic of near fault earthquake ground motion. Okay, no such pulse is obtained in far field earthquake ground motion. So this is the clear difference between near fault earthquake and far field earthquake, right? So what does this high velocity, long duration pulse does on the base isolated building, that we'll discuss. Okay. So, as we said that the near fault ground motion may have one or more velocity pulses with peak velocities of the order of 1 meter per second and duration of the range 1 to 3 seconds, right? Okay. So here, suppose we have designed base isolated system, suppose fixed base period is zero point 0.4 second, and to reduce the structural response, the structure is mounted on base isolation with time period, let us say 2.5 second, right? 2 second, 4 second. Now, when this base isolated building is subject to near field ground motion, right? We know for near field ground motion, there is a large velocity pulse with time period of the order of 1 to 3 second. So isolation period is 2.5 second, and the period of this pulse also in the similar range. So what happens? Resonance takes place, right? The frequency of external excitation matches with the frequency of superstructure. So in that case, base isolated structure may suffer extensive damage. Okay. So for this reason, the base isolation technology may be harmful when it is subject to the near fault ground earthquakes. Of course, there are some research is going on to improve performance of base isolated structure for near fault ground motion using semi-active control or active control, or using isolation bearing that exhibit adaptive behavior, etc. Now, see, in order to cope up the large isolation displacement demanded by near fault earthquake, in developed country, they are using special type of construction techniques. Okay, so let's understand what is this. See, the large pulses, these large pulses will have large impact on isolation system with a period in this range and can lead to a large isolator displacement. Okay, this is obvious. The large high velocity long duration pulse, when subject to the isolated structure, the isolated structure demands large isolator displacements, right? In order to accommodate large displacement, we can use this transfer truss. See, the upper portion, it shows the normal superstructure, and this superstructure is supported on transfer truss system. Okay, this particular part represent transfer truss system, and at bottom we can see isolation layer is provided. These are the isolators, right? So what is the advantage of using this system? See, when the superstructure is placed on transfer truss system, the number of isolator reduces, right? See, for this particular figure, there are total 24 columns, and usually we provide isolation bearing below the column. So using this truss system, the number of bearing has reduced to 8 bearing, so that this bearing can accommodate large displacement, right? So large displacement can be accommodated with the use of transfer truss system. Such type of system, this concept has been used in large building in Japan to take care of large isolator demand on the isolated system. Then another aspect for base isolated building is the inclusion of SSI. SSI is, we know it is soil structure interaction. So how the building, base isolated building responds when the flexibility of soil is taken into account. Okay. So we can see the influence of soil structure interaction are examined by studying the modal properties, that is mode shapes and natural frequencies of the isolated system. Now the effect of SSI on seismic response is small when the isolators are much more flexible than the soil. Okay. See, in SSI, we consider the flexibility of soil. So, if the flexibility of isolator is more than the flexibility of soil, then there is no effect of soil flexibility on base isolated building. However, when the flexibility of isolator and soil are close to each other or they are comparable, then the effect of SSI may be significant. That means the flexibility of soil may contribute to the building behavior. Okay. So this is regarding the effect of soil structure interaction. Means if the isolators are much more flexible than the soil, then the flexibility of soil have no effect on the overall seismic behavior of structure. However, when the flexibility of isolator and the flexibility of soil are nearly same, then the soil flexibility affect significantly to the structural behavior. In those cases, we have to take into account the soil structure interaction effects. Also, it is also observed that the cross interaction. What is cross interaction? It is the dynamic interaction among the multi-structure system through soil ground. Okay, normally this is possible when the buildings are constructed too closely, right? So existence of one building in close proximity may affect the response of the other building. Okay. So it is observed that the cross interaction between spread footing is not a significant factor for response in the fundamental mode. However, it can have considerable effect on the higher mode. So this is all about the influence of soil structure interaction in base isolated building. Then last point of the second part of our presentation, that is testing requirement of isolator. So before implementing the isolator in actual structure, it is always tested, and these are the few requirement of testing of isolator. IBC 2000 code requires that at least two full size specimen of each type of isolator be tested. The tests required are a specified sequence of horizontal cycles under this particular combination. Okay. It is as per IBC 2000, dead load plus 50% of the live load from small horizontal displacement up to the design displacement for maximum considered earthquake. In addition, the tests are also carried out for maximum vertical load, that is 1.2 dead load plus 50% live load plus Emax. What is Emax? Emax are the maximum downward and upward force isolated that can be generated during earthquake. And for minimum load of 0.8 dead load minus E minimum, which is the upward load generated due to the earthquake. So in addition to this, the testing requirement should also fulfill the second point. So here one figure is shown for the testing of isolator. Okay, it is a one test ring, and here you can see this is load beam, and in order to stiffen the load beam, the load stiffener is provided, and here you can see this is isolation bearing to be tested, and this actuator, it provides horizontal force, right? Then we have force transducer which measure the force, and we have two load cells. Okay. So first the isolation bearing is loaded vertically, and then horizontal force is applied, and it is tested to obtain the force deformation behavior, force deformation relationship. From the test result, influence of axial load and shear strain on bearing characteristic like shear stiffness, vertical stiffness, and damping behavior are obtained. And here is the example of typical force deformation behavior obtained from testing. So with this, we have finished the second part of our discussion. Now moving to the third part, design of base isolated building. How the base isolated building is designed. You know, here one picture is shown. Base isolated system consists of two main component, one superstructure component and the other isolation bearing. So the base isolated buildings are designed in two steps. In first step, isolation bearings are designed, and in second step, superstructure is designed. Okay. So let us see how the design is carried out. Same thing is mentioned here. The first step, design of isolator, and the second step, design of base isolated building. So let us see how the isolator is designed. Okay, of course, after doing that design, we have to check it. Okay, checking of design by non-linear time history analysis. So the third step is just for checking, whereas first and second steps are the design steps. So let us discuss how the isolator is designed. Okay, you can see this is first step, design of isolator. See, the objective of isolator design is to obtain equivalent stiffness and damping of the isolator. There can be many criteria for the design of isolator. However, we have these three criteria. Okay. See, the objective of isolation design is to obtain effective stiffness and effective damping. Okay. We can use these three criteria, right? It is interesting to understand each and every criteria. See, according to the first criteria, we can achieve good separation of time period between fixed base structure and base isolated structure. Okay. Normally, normally the time period of base isolated structure selected as per this particular criteria is around 3 to 4 times the fixed base time period. Okay. For example, suppose the fixed base time period is 0.5 second. Then how much time period should we take for base isolated building? That is around 3 to 4 times the time period of the fixed base building. Means if we select 3, then 3 multiplied by 0.5 is equal to 1.5. But as per UBC criteria, in no case the time period of base isolated building be less than 2 seconds. So let's discuss first criteria, good separation of time period. Okay. See, as per this criteria, the fundamental fixed base time period of superstructure is say TS. It is calculated from eigenvalue analysis. Then the isolation period TB is obtained as N multiplied by TS, means one constant multiplied by time period of superstructure. So that isolation period is well separated from the fixed base period of the superstructure. So typically N is selected around 3 to 4. However, in no case, the isolation period be kept less than 2 seconds as per the UBC criteria. Okay. So the first criteria is regarding this well separation, right? The building becomes flexible and spectral acceleration and base shear reduces drastically. Once the isolation period is decided based on equivalent damping of isolator, the spectral displacement and spectral acceleration of isolator are obtained from the design spectrum. Okay, the first part for the determination of isolation period is over. Once you know the isolation period, we can easily calculate spectral acceleration and spectral displacement using code-based spectra, right? It is shown here. Okay, two spectras are plotted. Okay, spectral displacement is here and spectral acceleration is here. So once you know the time period, see for example, if we take n is equal to 3 and the superstructure time period is 1.5, so 1.5 into 3, that is equal to 4.5. Okay, yes. So according to that, you can select of course 4.5 is not shown here. So you can select for 4.5 value, what is the spectral acceleration and what is the spectral displacement, right? So this is how the first criteria can be satisfied. Second criteria, specified maximum displacement of the isolator. See, in this criteria, we specify the isolator displacement, or we put restriction on the maximum isolator displacement based on practical consideration, right? Because we need to provide a gap or moat which is equal to the design isolator displacement. So that depends upon practical requirement. We can specify it, right? So for the second criterion, the permissible displacement of the isolator is specified from practical consideration. Then isolation period and spectral acceleration are obtained from the spectrum. Okay. See, here we can see, uh, you see, this is our design displacement. The design displacement is specified from practical consideration. For the particular example, we have selected that our design displacement is 20 centimeter. So we can draw one line corresponding to point 2 design displacement, and the intersecting point that represents the time period. Okay. See, in first criteria, we fixed the time period of isolation system, and then spectral displacement and spectral accelerations were obtained. Whereas in second criteria, we are doing something different. We are specifying the spectral displacement, and corresponding to that, we calculate the time period and spectral acceleration. Right? This is what mentioned here. So once you get this time period, the line can further extended above, like this. Okay, and we can obtain the spectral acceleration. So first we assume SD, and then we calculate TB and SA. Okay. So this is second criteria of designing the isolation system. Now third criteria. In third criteria, we specify the maximum spectral acceleration of the isolator, right? So for the third criteria, the spectral acceleration is specified from practical requirements. Okay. Then the isolation period and the spectral displacements are obtained from spectrum as shown in figure for assumed value of equivalent damping. Okay. Now this is very important. See, the third criteria is generally required for building containing sensitive equipment. Okay. For sensitive equipment, one should restrict the spectral acceleration, and machine that requires stringent control on the floor acceleration. And acceleration control may be required for human comfort as well. Okay. So when the building is hosting the sensitive equipments and machines, in those cases we have to follow this third criteria, specified maximum spectral acceleration. According to this criteria, we specify SA, and from SA we calculate TB and SD, right? So here we can see the specified acceleration is suppose this much, right? Then we extend this line, right? This is isolation period, and it intersect with spectral displacement graph over here. So the corresponding value for that is this. This is our SD, right? So let me to summarize quickly. In first criteria, what do? We first take TB, and then SD and SAR obtained. In second criteria, we specify SD, and from SD we obtain TB and SA. Whereas in third criteria, we specify SA, and then we calculate TB and SD. So that depends upon the requirement. So this is how the isolation system is designed. Okay. So the first part is over. Isolation system design is over. We will take one numerical example, and we will see how exactly the isolation system is designed in the next slide. Now the second part is regarding the design of base isolated building, right? For the preliminary design, the superstructure is assumed as a rigid block mounted on the isolator, and the superstructure isolation system is considered as a single degree of freedom system. Okay. Then the cross section of superstructure member are determined by equally distributing the base shear at all floors level, that we have explained that for base isolated building, the superstructure behaves as a rigid body, and hence the lateral force acting on all the floors are nearly same. Thereafter, the structural analysis of the superstructure is carried out as per the code provision, assuming it either as a plane frame or space frame. Further, the base of the frame is assumed as a fixed against rotation, vertical motion is restrained, and lateral displacements are controlled by lateral springs having stiffness equal to that of the isolator. Right? Then after doing the preliminary design of superstructure and isolators, a response spectrum analysis is carried out to obtain the better estimate of the isolator displacement. And if the displacement obtained from response spectrum analysis is less than the displacement considering as a rigid body, then our design is okay. Otherwise, if we get less amount of displacement from response spectrum analysis, then we have to modify the isolator property and we have to redesign the elements, and this step is repeated till convergence is achieved. Okay. So the peak displacement of base isolators are obtained from response spectrum method of analysis, and they are compared with those obtained from the preliminary design of the isolator. So here I am quickly summarizing the design process. First is design of isolation system that we know. Now for superstructure, what do? We assume the superstructure to be rigid. Okay. This is rigid superstructure, right? And we got some bases here. Okay, we are taking the example of 1, 2, and 3 storied building. So what do in this case? This base shear will be equally distributed, right? So VB by 4, VB by 4 at all floor levels. Then these forces are assumed to act on each floor. These are the lateral forces: 1, 2, 3, 4, 1, 2, 3, 4, 5. I draw, see, let me to cancel it. 1, 2, 3, 4. Right. Let us assume that one intermediate column is also there. Now here, what do? We put roller support for analysis, right? And suppose there are n number of bearings, and the stiffness of one bearing is K effective. So total stiffness at base of building will be n multiplied by K effective. So the isolators are modeled by providing a spring whose stiffness is equal to n multiplied by K effective, and all the floors will be given equal base shear, right? So now we can do the analysis of structure using our normal softwares. No need to perform any sort of nonlinear analysis. So we can take different case: dead load, live load, earthquake case, etc. And the normal structural analysis is carried out, and the members are designed, beam, column, etc. They are designed as usual. So once the design is over, the designed structure is further checked by performing RSA, response spectrum analysis. And the response spectrum analysis results should be conservative as compared to the preliminary design of the isolators, preliminary design of the superstructure and isolator. Right. So same thing is mentioned. If the significant difference between the two is found, the isolator characteristics are modified and the response spectrum analysis is repeated. This process is continued till convergence is achieved. Then in the last step, the results are checked by performing nonlinear analysis. Okay. So nonlinear analysis is carried out. And again, if there is a significant difference between the response spectrum analysis and nonlinear analysis is there, then we have to revise the properties of isolator and superstructure, and further reanalysis is carried out till the convergence is achieved. So once the design pass through nonlinear time history analysis, then it is okay. So here one simple example is given that shows how the lead rubber bearing is designed. So we will move very quickly. See, there is one building, 5-storied building, and it has 1, 2, 3, and 4 bays. Right. The building is located in seismic zone number 5. Okay. So design lead rubber bearing for 5-storied building using IS 1893 specification Consider 10% damping ratio, and ratio of pre to post yield stiffness of isolator is 10. Reaction at interior column is found 800 kilonewton for dead load plus live load condition, and fixed base time period of building is 0.85 second. Bay width and story height is given. So design of LRB is a two-step process. In first step, isolator properties are calculated. Which isolator properties? Effective stiffness, design displacement, characteristic strength, post yield stiffness, and yield displacements are calculated first. And then in second step, calculation of sizing of the elements of isolators are carried out. That means what will be the diameter of the bearing, what will be the height, what will be the diameter of central lead core, etc. What will be the thickness of rubber and steel layer, etc. That is called geometric design. So in first part, these properties are calculated, and in second part, the geometric design is carried out. Okay. So it's a typical force deformation relationship of lead rubber bearing. This particular behavior is called bilinear behavior. Okay, because it has two stiffness. This is called primary stiffness, and this is secondary stiffness. Secondary stiffness is K2, here it is mentioned, and primary stiffness is K1. And other parameters, Q is called characteristic strength. This is the characteristic strength. Fy is the yield strength. Then dy is the yield displacement, and dmax is the maximum displacement, or we can say it is design displacement for which the isolator is designed. Then the isolator properties are calculated using this step. First, we find the effective stiffness, then design displacement. It is spectral acceleration multiplied by zone factor, then damping modification factor, and isolation period, and I is important factor. Okay, we are familiar with all this terminology. And characteristic strength, secondary step, stiffness, and yield displacements are calculated using this formula. Okay, and finally we can have the design. See, this particular figure represents the designed lead rubber bearing for the 5-storied 3-4 base building that we show in previous slide. Okay, so this is the exact design bearing. The diameter is 500 millimeter. Okay, after using all mathematical equations, we got this. Height of the bearing is again 500 millimeter. 25 mm thick cover plates are there. Then 50 mm dia lead core is sufficient for this design, and the thickness of rubber layer is 12.5 millimeter, and that of steel plate is equal to 2.5 millimeter. So this is how the bearing is designed. And this is well-known photograph of Bhuj Hospital, newly constructed building. We are not discussing much more about this because we all know. Then here is the second example of base isolated building called demonstration building in Indonesia, which was constructed using lead rubber bearing 1994. It's a ground plus 3-storied isolated building. And here we can see the services, and we need to provide flexible, costly connections for the services. Then this figure shows the application of base isolation in bridge. Right here, the isolation bearing is provided between the deck and superstructure. Right, and last, it is a San Francisco City Hall. The base isolation is used as a retrofitting strategy. This is very interesting. We'll move very quickly over this. See, this building was constructed in San Francisco in 1915, right? The fixed base period of this building is 0.9 seconds. So it is a very rigid type building. It sustained the substantial damage from 1989 Loma Prieta earthquake, which was centered about 600 miles away, and the structure was damaged, which necessitated repairs and strengthening. Now, it's a historic type building, and in order to preserve historic fabric of the building, base isolation was adapted to improve the seismic resistance. Right. The superstructure was strengthened by new shear wall inside the building so that externally it appears as it is. So the existing fixed base building was retrofitted using base isolation technology. For that, 530 lead rubber bearings were used, and which resulted in isolation period of 2.5 seconds. Note, compare it with the fixed base period. And the retrofit project was completed in 1998. So base isolation is not only used for constructing new building, it can also be used for as a retrofitting option. In summary, most suitable candidates for seismic base isolations are steep structures on hard soil underneath, such as low rise building and medium rise building, nuclear power plant, bridges, large liquid storage tank, and many other types of equipment. High rise buildings are not suitable for base isolation due to its high fundamental period. For building rested on very soft soil, base isolation is not suitable as it shifts structural fundamental period into more critical range. It rather magnifies the structural response. In general, only certain type of structures are presently suited for base isolation, although technology is gradually overcoming these limitations. So these are the few references which were referred to prepare this presentation. And this brings the end of our today's discussion. Thanks for your patience hearing. Thank you.
Thank you very much, sir, for your nice presentation with core depth of understanding regarding the application of base isolation. Sir, we have the active audience, so they have some of the questions. So we have short of time, but quickly we will try to give maximum answers. So first question is, sir, the kind of bearing used in Bhuj Hospital is
It is
uh,
lead rubber bearing, LRB.
LRB. It is lead rubber bearing. Okay. So next question is, what is mushroom shape basement? Uh,
Mushroom shaped basement.
yeah. Um,
See here, I try to draw mushroom shaped basement. It
hmm,
is something like this. Superstructure, these are the different floors, and mushrooms, they are provided like this. Okay, there is a pin type connection over here,
hmm.
so that the upper portion swings like this. Okay, it swings to and fro in this direction. This is called mushroom type isolation system.
Okay, sir. Uh, so next question is, in 3D structure, what is the behavior of isolator in torsional mode of vibration? Can we design it for that?
Yes, it can be designed for torsion. See, I showed one last figure that the superstructure is modeled resting on rollers, and equivalent stiffness of isolator is applied in horizontal direction, and then the analysis is carried out in usual way. If it is a, torsionally coupled system, then the lateral forces will be calculated accordingly depending upon the distribution of mass and stiffness.
Right, sir, right. So next question is the base isolation isolator is effective for vertical ground motion too?
Yes, it is very much effective in vertical ground motion because
Uh,
the isolation system has infinite vertical stiffness, right?
hmm.
So, so far as that LRB and rubber type bearing is concerned, it is very much effective. However, for friction type isolator,
Okay. Okay, sir. Sir, could you use the base isolator in a soft or loose soil with raft foundation with considerable damping? Um, hello? Hello? Um, sir, your voice is not audible. Hello?
hello.
Yes, sir. Yes, sir. Uh, sir, is the base isolation is effective in soft and loose soil with raft foundation?
No, not at all. We have discussed it using the response spectra. For
Yeah.
soft soil, it is not effective. In fact, soft soil is not good candidate for base isolation.
Okay. Can we use base isolation system for long span roof truss frame subjected to vertical ground motion?
Yes, so far as rigid structure is concerned, if a long span truss is having low time period, fixed base period, then we can go for base isolation.
Okay, sir. Is the base isolation is more flexible? If the base isolation is more flexible, will it be more efficient?
No, not like that. Because see, higher is the flexibility, higher would be the displacement at the isolation level, right? So
Right.
we need to design costly flexible connections for utility, and even we have to provide large space to be used at moat. So this is not advisable.
Okay. Uh, while doing the nonlinear time history analysis, how to consider the time history since there will be a considerable vibration in motion?
For that, many research is going on regarding the selection of time history for nonlinear analysis. That is a specialized subject, and we can find relevant information because it requires time to explain each and everything of ground motion selection. It's another topic of discussion.
Okay, sure, sir. Uh, Sir, can the base isolation be provided to very tall structures like chimney or cooling towers, like ND cities, etc.? If yes, then what precautions to be taken while designing the structure?
No, as we have seen that base isolation is not suitable for flexible structure because flexible structure have already high time period. And when such structures are placed on base isolation, their time period will further increase. And we know the nature of response spectra. One, it has entered into the displacement sensitive region. There is no significant reduction in spectral acceleration, even significant increase in time period. So for tall structure or flexible structure, base isolation is not suitable. We can go for other alternative like tune mass damper and other sort of energy dissipation devices can be used.
Okay. Sir, what are the key parameters for newly developed base isolation techniques?
Key parameters in terms of what isolation system or
As per the question, I understand is suppose any new isolation system is to be designed,
uh,
which parameters will be most effective in design of the structure itself?
huh. See, further that depends upon the requirement. The
Yeah.
first parameter is the selection of type of isolation system, whether it is a friction type system or rubber type system. Second parameter is the site location of building, whether it is located in the proximity of active fault regions or no, or not. Third parameter is regarding the soil condition. The fourth parameter is regarding the geology of the soil between the source of earthquake and the site on which the building is constructed.
Okay. What are the effect of foundation of building by providing base isolation? Is it differ
Effect of
from general fixed base building foundation?
no, no. I'm coming answering this question at last. Let other questions to address because I wanted to show one slide for that.
Sure, sure. SAP 2000 for nonlinear dynamic analysis, which type of stiffness of isolator used for input parameters?
Effective stiffness for in SAP 2000 analysis, you need two type of stiffnesses: linear stiffness and non-linear stiffness.
Yeah,
Linear stiffness is K effective, right? And I showed the equation. K effective is nothing but m into omega square, where m is the total mass of the superstructure plus mass of the base, and
yeah.
omega is equal to 2 pi upon tb, time period of the base isolated structure. So that is effective, which can be easily calculated, right? And for non-linear parameter, we need secondary stiffness K2. Okay, in force deformation behavior, I showed that graph that initial stiffness is K1 and the secondary stiffness is K2. So that K2 stiffness is also required in SAP model. So these parameters are required for modeling isolated system in SAP 2000.
Right, sir. What could be the maximum time considered for base isolated buildings? Uh, I
It
think,
can be 4 seconds, or even it can be 5 seconds for certain type of structure.
yeah. For closely spaced structures, base isolation will affect the adjacent structure. For that, we have to make the base isolation rigid. How effective is that?
See, for closed spaced structure, closely spaced mode shape, it is a property of superstructure,
Right.
right? And we have seen that when the superstructure is placed on isolator, it behaves as a rigid body, right? So everything is governed by the isolation mode itself.
Mhm.
Okay, so I hope this answers to this question.
Right, sir. Uh, Only time history analysis is carried out, or response spectrum analysis will also have to be carried out.
No, we have discussed
Yeah.
there are three steps of design. First, preliminary design. After doing that, we need to perform response spectrum analysis, in which we assume isolation system as a linear. Okay, you remember we draw one spring having K effective stiffness. That
Right.
isolation was assumed linear, and after doing that response spectrum analysis, for the purpose of checking nonlinear time history analysis is carried out.
Okay. There is some modeling question. Which type of support has to be assigned in analysis for structure with base isolation?
That's what we showed: roller and then equivalent spring
Yeah,
for
right.
linear analysis. And for non-linear analysis, we have to model the isolation system in professional software.
Right, sir. And the last question is the Manipur state is a luxuriant plain, so soil are moderately soft as well as falls in seismic zone 5, and 90% of the geographical area of the state is hilly. How can we provide base isolation in this condition? Can base isolation be provided on uh, hill sloped buildings?
Yes, we can provide, but for the foundation of building, we need to do some sort of special treatment, like rubber soiling and other sort of special treatment is to be done before constructing the foundation for building.
Right, sir, right. The last question newly came is the friction pendulum isolator analysis in SEP 2000 in nonlinear dynamic analysis, which stiffness is used? Is that the post yield stiffness of isolator?
Post yield stiffness, see, I'm explaining the force deformation behavior of friction pendulum system is like this,
Right,
right? And we need to give this stiffness K2, right? And for FPS only, K2 is equal to M into omega square, 2 pi upon TB whole
mhm,
square, where M is the total mass of base plus superstructure, and
mhm,
TB is the isolation period. Suppose
mhm.
you need to design isolation system for 2.5 seconds, you put TB equal to this, take mass, you will get K2 stiffness. And this stiffness is directly given as a SAP input.
Right. Uh, so that's all. I think all the questions are covered. One
Ah,
answer that is
at,
pending.
at last, I am showing one
Yeah.
slide here.
Yes.
Yes, this is very interesting.
Mm,
Summary of basic building cost. Okay, a three-storied building, 180 feet by 120 feet plan dimension. Of course, the estimation is carried out based on 2008 market rate in US, but this will serve our purpose to see how much percentage increase or decrease is there when we go for the base isolation system. Okay, this is regarding foundation. Foundation, we can see there is a huge increase of cost, 34.3, because we have to construct some special sort of column stubs, and very precise, accurate work needs to be carried out. So for base isolation, foundation cost increased by 34%. However, the structural elements becomes lighter, and there is a reduction in the cost of structural element by 30.3%. Then isolation layer itself has some amount, right? Then non-structural element, the cost is increased by 2% because very high performance standards are expected for base isolated structure. Then elevators, mechanical and electrical item, there is increase in 6.4%. So total building and site cost is coming 9.3%. Okay. So this is the point which I wanted to highlight. The foundation part is very much important for base isolated building.
Yes, sir. Yes, sir.
So
So I think we have very much active audience and almost all the questions that we have answered. So we hope that the session the participants have found very much useful and knowledgeable. So thank you, sir. Thank you very much on behalf of Marwadi Education Foundation as well as Atal Academy. Uh, even after, if the participant is having any question, you may mail us. We may try to get the answer from the sir.
sure,
And
sure.
yeah, okay.
Okay.
Uh, okay, so we end this session and participants are requested to join for the next session in 5 minutes. At 11:40 we will start. Okay, so you can have a break for 3-4 minutes and we'll start at 11:40. Yeah. Thank you, sir. Thank
Thank
you once
you.
again.
Thank you very much.
Ji, sir.